Welcome back, everybody. So it's a pleasure for our second talk of the afternoon to have Amos Nevo from Technion, the University of Chicago, who, as you can see, is going to talk to us about optimal Diophantine approximation on semi-simple algebraic groups, temperedness and density of unitary representations.
Thank you very much, Martin. And I really would like to start by expressing my thanks to the organizing committee and the scientific committee of the TIFR International Colloquium. I'm really sorry that I was not able to come in person. I was looking forward to visiting India for a long time. It's been a few years since I visited, but unfortunately there were some unforeseen developments and all of my flights were canceled and I couldn't really come. But I'm very grateful for this opportunity to talk about this subject. This is going to be based on joint work with Anish, Ghosh, and Alex Gorodnik, and on joint work with Mikolaj, Fraczyk, and Alex Gorodnik. And the subject is going to be optimal Diophantine approximation. So let's start with our setup. The general topic we're going to discuss is lattice actions on homogeneous algebraic varieties. So let's set it up as follows. G will be a non-compact semi-simple linear algebraic group of SLN-R defined over Q. We all know, of course, a lot of simple examples of this setup. And gamma in G will be an irreducible arithmetic lattice subgroups of G. Sometimes gamma will be the integer points in G, but that's not necessarily the case. And we consider an affine algebraic subvariety V in Rn, which is defined over Q, and which is invariant and homogeneous under the G action. So G, of course, acts on Rn as a subgroup of SLN, and there is an invariant variety under G, and this variety is homogeneous. This means that V is of the form G modulo H, and there is some stability group H, which we assume to be a non-compact algebraic subgroup defined over Q. So that's what defines this algebraic variety. And we assume also that H is unimodular. And since G is unimodular, this means that V carries a G invariant measure M. Finally, we assume that the gamma action on V is ergodic with respect to this natural G invariant measure. And it follows by very general considerations in ergodic theory, which are very simple, that then almost every gamma orbit is dense in V. And the topic that we're going to pay attention to is you look at this action of gamma on V. This gamma has dense orbits, and in fact, almost every orbit is dense. And generally speaking, the question is, how dense is it? So how do we give an answer to this question? Sorry about this. Yes. Before we do, let's take a look at some of the examples that come up, examples of rational homogeneous varieties. One of them, of course, is the unit sphere, definitely. We can consider also the one-sheeted hyperboloid in R3, and we can consider the two-sheeted hyperboloid, which are very different, of course. We can consider the variety of unimodular matrices, 2x2 matrices whose determinant is 1. We can consider the variety of orthogonal matrices, and we can consider general quadratic varieties, which would include rational ellipsoids and hyperboloids given by a quadratic equation. The sum I goes from 1 to k of ai xi squared equals m, with ai and m being integers. And we can consider group varieties, which will be our main topic today, at least later on. And we can consider principal homogeneous spaces. For example, we can consider the constant determinant variety det x equals m. And there is a whole variety of other varieties, symmetric varieties, spherical varieties, reductive homogeneous spaces. It's a very rich topic. And I should say that we're not going to put the emphasis on this today, but what we have here is a collection of dynamical systems. We have a certain countable group gamma acting on such spaces. But actually, from the dynamical point of view, this is really very diverse. Some of these actions, for example, on the sphere, let's say, can be isometric actions, and this would be the same for the two-sheeted hyperboloid. Others are definitely not isometric. Like on the one-sheeted hyperboloid, it could be that every orbit of gamma is dense, or it could be that it is genuinely the case that only almost every orbit is dense. From the dynamical point of view, this is a very rich topic. But there is one underlying question that we would like, or there's more, but there's the underlying question that we would like to consider today is how do we quantify the denseness of dense orbits? And so we fix a norm on Rn and on MNR, and we restrict the norm on Rn to our invariant variety V. And for xx naught in V, we consider the Diophantine inequality the norm of gamma inverse x minus x naught less than epsilon. Now, by definition, for almost every x, it can be solved. Namely, we can find a gamma for every x naught. This is simply the same thing as the denseness of the gamma orbit of x, which accounts for this. But suppose that for some pair xx naught in V, a solution gamma in gamma exists, satisfying the norm bound, norm gamma less than or equal than some constant b times epsilon to the minus zeta for all sufficiently small epsilon. And then we can define the Diophantine approximation exponent kappa xx naught as the infimum of zeta positive, such that the foregoing inequality has a solution with these properties, with these bounds. So you can see that this is a really very general definition. Now, in our setup and under simple assumptions, which are certainly valid for norms, this function kxx naught is a gamma times gamma invariant function, and by ergodicity, it is then almost surely constant. And so in that case, we can define kappa gh gamma to be the almost sure Diophantine approximation exponent for the gamma action on G mod H. And that's a number that measures the density of a typical dense orbit in the variety, typical in the sense of measure, namely typical in the sense that it holds in a co-null set. I should mention that it would be definitely as interesting to consider the, I guess I should call it the uniform Diophantine approximation exponent, meaning the exponent that will bound every single orbit, if in fact it is the case that every single orbit is dense. This is a very, very interesting problem, but it is a problem. There are very few instances of this, and it's very difficult. The almost sure Diophantine approximation exponent is more approachable, and this will be our topic today. Let me make the following very brief remarks that the problem of establishing the Diophantine approximation properties of typical points on a homogeneous algebraic variety G mod H, when G is semi-simple, and you could say more generally, was raised by Serge Lang in 1965. The points allowed by the approximation process that was raised by Lang are the rational points on the variety itself. So this problem would appear to be separate than the one we are considering, but actually when H is semi-simple, these points constitute finitely many orbits under the action of arithmetic lattice gamma in G, which is part of the Borel-Harischandra theorem of 1961, I think. And so it turns out that for some varieties, certainly not for all varieties, but for some varieties, this problem of Diophantine approximation raised by Lang is really the same as the problem of the of gauging the density of lattice orbits on the corresponding homogeneous space, the corresponding algebraic variety. One basic Diophantine property is the size of the approximation exponent, which is a quantitative gauge of the density of the orbits of that arithmetic lattice acting on the rational algebraic variety G mod H. But actually, Lang had several other Diophantine properties in mind, and he even mentioned them in that in that survey that he wrote. So more refined Diophantine properties include an analog of Khinchin's theorem from classical Diophantine approximation in Rn, and more ambitiously, an analog of Schmidt's theorem, Wolfgang Schmidt's theorem, effectively counting the solutions to Khinchin's theorem. And Lang quotes this theorem very approvingly in his survey. It was very recent at the time. And another possible Diophantine property, which was not mentioned by Lang, is effective estimates of discrepancy of rational and algebraic points. And all of these, of course, are very, very interesting and quite challenging. Some progress has been made on some of these problems, but I'm not going to discuss it today. Let me say very briefly, perhaps way too briefly, about some previous approaches to this problem. So it's no surprise that for some specific classes of homogeneous algebraic variety, the exponent of approximation, and actually also the discrepancy, were studied for a long time using several different methods. The varieties involved include the Euclidean spheres, a very time-honored topic, general ellipsoids, and more recently, non-compact quadratic varieties. And there are perhaps some other similar examples, but just to mention some of the methods involved in this analysis include estimates of exponential sums, and then estimates of automorphic forms and of Hecke operators, and more recently, methods of homogeneous dynamics, and particularly the analysis of cusp excursions of diagonalizable flows. But okay, this is a very substantial topic, and I'm not going to attempt to give any kind of survey, or even a lot less than a survey. Our goal here is to describe very briefly an approach to obtaining Diophantine approximation results on general varieties, including optimal Diophantine exponents in some cases, which utilizes spectral theory of unitary representations of semi-simple groups. So that's going to be our topic. Okay, so let's start with a few brief comments on the lower bound. how do you obtain a lower bound for the Diophantine exponent? And so for this, assume that the stability group H, the volume growth of the norm balls, HT, which is H in H such that norm H is less than T, is essentially T to the some constant A, some positive constant A. The Haar measure MH of the norm ball HT is between T to the A plus eta and T to the A minus eta. And then utilizing a coarse solution to the lattice point counting problem, it follows that the number of lattice points in the intersection gamma intersect a norm ball HCT, translated on the left by some element G in G what's the word? Expanded on the right by C inverse, where C is open and bounded. So the number of lattice points in this open set, bounded open set, is at most T to the A plus eta with certain constants involved. For that, you need a very general coarse solution of the lattice point counting problem, but that can be obtained in great generality. Now, what is the significance of this set GHCT times C inverse? If gamma is of that form, GHC inverse, that means that gamma inverse GH belongs to CH under the projection to G mod H. And so if C is a neighborhood, if CH contains some observation point X naught, then we're looking at the situation where gamma inverse GH has been transformed, has been transported to a neighborhood of some other point, let's say G naught H, or the coset G naught H in G mod H. And so, on the other hand, if the dimension of our variety is D, then there are at least epsilon to the minus D plus eta disjoint epsilon ball in an open neighborhood CH of a point in G mod H. And so the number of elements gamma in gamma of norm at most, well, CT or T, let's say, which are going to take GH to a neighborhood C capital H of our point G naught, is bounded by T to the A, and that's the number of pigeons, and the number of pigeonholes is at least epsilon to the minus D. That means there are that many disjoint epsilon balls in an open neighborhood of that point. And so from this, using a volume packing pigeonhole argument, we can conclude that the Diophantine exponent obey the following lower bound. Kappa is at least D over A. In general, you cannot approximate by using matrices of smaller norm. This is the limit of how successful you're going to be. And one should mention that this bound is really truly general, and it is independent of spectral theory and essentially most other things. And it holds in great generality. So I don't know, I mean, perhaps one can formulate an even more general conjecture, but okay. So this can be obtained, except perhaps for the solution of the lattice point counting problem, by elementary means. And now we would like to try to strive for an upper bound. And for an upper bound, we will use spectral estimates of ergodic averages in the automorphic representation. And so let G act by measure-preserving translations on the probability space G mod gamma with respect to Haar probability Haar measure on it, Haar probability measure on it. And as we all know, this action gives rise to the automorphic unitary representation pi g mod gamma from G to the unitary group of the Hilbert space L2 G mod gamma by pi g fx equals fxg, namely we translate on the right. Now, the averaging operator beta t associated to a subset ht, which is the norm ball contained in H, which is a subgroup of G, is a generalization of the classical ergodic average. We defined it as follows. It is defined by sampling the values of a function along the orbits of H in G mod gamma, along the orbits of H up to time t. Of course, time here is, I don't know, just a suggestion. It means that you average the orbit, you average on H on the norm ball ht. So this is like averaging up to time t in the classical situation. And so by pi beta tfx is the integral over H in ht of fxh. We translate x by h for all H in the norm ball, take the integral with respect to Haar measure mh, and then we normalize by the total Haar measure of the norm ball ht. If you think about it, this is the classical, this is the direct generalization of the classical ergodic average that you would use, for example, for flows where the acting group is the real line, maybe disks in R2 when the acting group is the plane, etc. And now suppose that the automorphic representation of G in the space of functions of zero mean has a strong spectral gap. That's very important in the case of semi-simple rather than simple groups. And that simply means that every simple component has a spectral gap. That's a very important assumption, but it's really quite often the case. And when you have a strong spectral gap, then the restriction of the representation pi naught G mod gamma on L2 naught to any non-compact semi-simple subgroup H of G has the same property, namely the strong spectral gap, and then the following result applies. We have an effective mean ergodic theorem for the averages beta t, which we can formulate as follows. So let the ergodic action of a semi-simple algebraic group H on the probability space X have a strong spectral gap. Then the convergence of the averages along the H orbit to the space average on X takes place at a rate given by a negative power of the volume. And so pi beta Tf, this is in classical ergodic theory usually called the time average along the orbit, minus the space average, namely the integral over x of f d mu. This has a certain norm bound in L2, and the norm bound is some constant times the volume of the norm ball to a certain negative power. And the validity of this mean ergodic theorem actually requires only that the volume of ht goes to infinity. It's not dependent on any specific properties of ht, but it certainly applies in our case. Okay, and so just to repeat, we assume that the automorphic representation of G in L2 naught G mod gamma has a strong spectral gap. This will be inherited by our semi-simple subgroup H. And in that case, the averages that we defined, the averages along the orbit, they will satisfy a remarkable property, and this remarkable property is a feature of unitary representation theory of semi-simple groups, namely the convergence of these ergodic averages will take place at an effective definite rate, which is a negative power of the volume. And now we would like an upper bound for the Diophantine exponent. And we can appeal to an effective duality principle, which states that the exponent of approximation of the gamma orbits in G mod H, namely the effective rate of density, is controlled by the rate of convergence of the averages supported on the H orbits in G mod gamma to the ergodic mean. So maybe I should say one word about the duality principle. Well, the duality principle in homogeneous dynamics is a long-standing heuristic, which I'm going to formulate in the following way. The heuristic is that if you want to study anything about the gamma orbits in G mod H, so you have three bits, which is the group G, the subgroup H, and the lattice gamma. And if you want to study the gamma orbits in G mod H, the gamma orbits in G mod H, it is likely to be to your advantage to study the H orbits in G mod gamma. And this duality principle has a lot of instances, and it goes back a number of decades, but it hasn't been exhausted. And what we are talking about here is a certain effective duality principle, which in this particular case says that if you want the exponent of approximation of the gamma orbits in G mod H, the dual property that will come to your rescue is a rate of convergence of the averages along the H orbits in G mod gamma. So this has to be proved, of course, but okay, so now the convergence of the averages supported on H orbits in G mod gamma is the same thing as the rate of convergence theta in the effective mean ergodic theorem. So this theta is what we call the rate of convergence along the gamma orbits. And as a result, we have the following result. The Diophantine exponent, kappa, obeys the following upper bound. So kappa is bounded by 1 over 2 theta times d over a, same d over a that we had before. And so the conclusion is that if 2 theta equals 1, so 2 theta equals 1 when the rate of convergence in the effective ergodic theorem is the reciprocal of the square root of the volume of the averaging set HT. So, okay, theta equals 1/2 in this case is 1 over the square root of the volume. And so 2 theta equals 1 when this is our rate of convergence. And when that happens, the lower and the upper bounds for the Diophantine exponent coincide. And the a priori pigeonhole bound d over a is optimal. Okay, so that's very nice because it's a very concrete criterion. The only wrinkle, of course, is that you have to come up with some explanation of when is 2 theta equals 1 actually going to happen. So let's repeat that in an equivalent form. So suppose, or well, not equivalent, but a sufficient condition, suppose that the stability group H is semi-simple. And suppose that the restriction of that automorphic representation pi to H is in fact weakly contained in the regular representation of H. Namely, in other words, it is so-called tempered representation on H. And then the operators beta t satisfy the best possible spectral estimate in the automorphic representation of G on L2 G mod gamma. That best possible estimate is the estimate that holds in the regular representation of H. Okay, so this may be, I mean, I'm sure this is familiar to many people. This, in general, you know, it requires some explanation, but the regular representation of a semi-simple group is the representation which has the best spectral estimate of all the unitary representations. And what we're doing here is that we are formulating a sufficient condition for when theta equals 1/2 or 2 theta equals 1. Namely, we are estimating ultimately operators supported on a subgroup H. And so we are interested in the restriction of our unitary representation to the group H. And we are assuming that that restricted representation satisfies the best possible spectral estimate for representations of H. So, okay, you can say that this is a lot to assume, but what we know so far is that in that case, the lower and the upper bound of the Diophantine exponent of the irreducible lattice gamma in its action on G mod H will coincide so that it is best possible and given by kappa equals D over A. The reason for that is that in the regular representation, it is in fact the case that the norm bound satisfied by the operators beta t is that they have decay, which is 1 over the square root of the volume. And the underlying reason why that is true is in a very, very famous and very famous theorem about analysis on semi-simple Lie groups, which is the so-called Kunzi-Stein phenomenon, which has been around for a long time, but we drafted here in order to estimate our operators. Okay, and so now what we would like to say but not demonstrate is that it is a remarkable feature of unitary representation theory of semi-simple groups that the foregoing condition of subgroup temperedness, and let me repeat this again, subgroup temperedness means that the subgroup H, when you restrict the unitary representation of G to it, has the best possible spectral estimate that it can have. So it's a very, very powerful and meaningful condition. And subgroup temperedness holds, in fact, in considerable generality for a large class of triples, GH gamma. This is a very nice topic in its own, and I would be happy to expand on it. But this is not our topic today, and so I'm only going to say that we are all very familiar with an instance of this fact. And, well, I don't know, okay, let me say a time-honored instance. I don't know if I would say it's the first, but anyway, those of you who are familiar with Kazhdan's original proof of property T in 1967 in his 3-page paper will remember that actually what Kazhdan proved, well, actually the method of proof of property T by Kazhdan involved the remarkable observation that if you take G to be SL3R and H to be SL2R, and it is embedded as in the upper left-hand corner. So this is definitely a situation that conforms to our assumptions. G is simple, H is simple. Algebraic groups defined over Q. Well, then, in fact, if you restrict any representation of SL3, which does not have invariant unit vectors, to SL2, then you get some representation of SL2, but it turns out this representation of SL2 is tempered. So the unitary representation of SL2, given by any restriction from SL3, has this best possible spectral estimate. This appears explicitly without any without any further explanation needed in Kazhdan's original paper. So we can now draw the conclusion, if you are interested in the algebraic variety, SL3R modulo SL2R, which is a nice algebraic variety, every lattice in SL3R acts on it with best possible Diophantine exponent. And that best possible Diophantine exponent is D over A. And so, yes, so it's 5 over 3 in this case. So Kazhdan's original argument has been greatly expanded since then, but in fact, in unitary representation theory, there are several other general principles which actually guarantee subgroup temperedness. One can use the whole theory of universal pointwise bounds for matrix coefficients of representations. And sometimes it gives you that when you restrict such a universal lower bound to a subgroup, then you get a universal bound which is in L2 or L2 plus epsilon of the subgroup, and that would be sufficient for subgroup temperedness. There is a very important general principle developed by Margulis, which will tell you, which will also produce subgroup temperedness. And so it's actually quite remarkable how often this remarkable best possible spectral estimate actually holds. Having said all that, what I would like to do now is to try to move beyond this condition, the condition of subgroup temperedness. And so while temperedness of the restriction of the automorphic representation of G on G mod gamma to a subgroup H is a common occurrence, it definitely fails in some important cases. For example, if G is SL2 times SL2 and gamma is an irreducible uniform lattice, then the automorphic representation of G has a strong spectral gap. This sounds like an innocent statement, but actually there is a lot that needs to be proved here. But that is in fact the case. And in fact, it is conjectured to be tempered. L2 G mod gamma is conjectured to be tempered, but only conjectured. If you take H to be SO2 cross SL2, and that would give you that G mod H is nothing other than the hyperbolic plane, then the restriction is not known to be tempered. You could say that it's conjectured to be tempered, but that is really very remote. In fact, temperedness in this case amounts to the validity of an analog of Selberg's conjecture in this case, and it is expected to hold, but this is very challenging and really quite remote. So what do you do in this case? Now, dynamically, I should mention that the problem amounts to Diophantine approximation on the hyperbolic plane, H2 equals G mod H by elements of a uniform irreducible quaternion lattice. So the irreducible lattices of SL2R cross SL2R are, in fact, arithmetic. That's a theorem of Margulis. And if they are uniform, then there is an associated quaternion algebra which underlies, well, with which they're associated. And so this is a very nice, very direct Diophantine approximation problem, but it will not be solved by the method that I indicated previously until you proved the Selberg conjecture in this case, or something very close to it. So the question is it possible to establish optimal exponents without assuming temperedness of the age representation, circumventing analogs of the Selberg conjecture? Okay, so for that, we have to mention a very profound insight, which is due to Peter Sarnak a long time ago. So let's start as follows. So in the case of a uniform lattice, which we will take from now on because otherwise the analysis needs a great deal of further development. So in the case of uniform lattices, the automorphic representation decomposes to a countable discrete sum of irreducible representations, each with finite multiplicity. That's general functional analysis. And an important conjecture formulated by Sarnak, the density conjecture, is based on the heuristic that even if we allow the possibility that non-tempered representation appear in the unitary automorphic spectrum, still their multiplicity must decay directly in relation to their exponent of integrability, namely their degree of non-temperedness. Let me maybe elaborate on this very briefly. So we saw that non-tempered representation was the enemy of the previous method. And since the previous method really only took into account the operator norm of our averaging operators beta t, even the existence of one non-tempered representation is disastrous. But maybe we can develop a more tolerant method, which will say, well, yes, you do have in principle perhaps the occurrence of non-tempered representation, but what you should do is not take the uniform operator norm. You should develop a different spectral approach, and this spectral approach, it will take into account that the multiplicity must go down if the degree of non-temperedness goes up. Now, the most highly non-tempered representation, I should say, is the trivial representation. And in the case of a lattice, the trivial representation actually occurs only once. Okay. And so the heuristics is that representations which are non-tempered and in some sense, or in the Feld topology sense, are close to the trivial representation, they may perhaps occur, but their occurrence, they don't occur very much. Their multiplicity is low. And so this implies that the combined spectral contribution of the non-tempered representation can be controlled and used to estimate the Hilbert-Schmidt norm of suitable geometric convolution operators in the automorphic representations. So let me... sorry?
So we lost you for a while, Amos. So we lost you after your second bullet point on this slide.
So only the third?
Yeah, if you could go over the third bullet point again, that'd be good.
Yeah. Okay, so the second one said that maybe non-tempered representation occurs, but if Sarnak is correct, if Sarnak's conjecture is correct, then they appear only rarely or with low multiplicity. And this implies that if you develop the right spectral approach, the combined spectral contribution of the non-tempered representation can be controlled spectrally and used to estimate the Hilbert-Schmidt norm of suitable convolution operators in the automorphic representations. If you want it to be formulated in the most technical way, you can say that we trade in the uniform operator norm that we used previously in the method we trade it for the Hilbert-Schmidt norm in L2 of G mod gamma. So this is the most technical aspect of it, but there's considerable analysis that needs to be developed. And so let me mention recent optimal exponent using density estimates. So in very recent work, which is not published yet, the optimal exponent was established for uniform quaternion lattice in joint work with Fraczyk and Gorodnik. And here we have been using an Archimedean version of the Sarnak density conjecture, proved for this case for the case of uniform quaternion lattices by Fraczyk, Harkos, Maga, and Milicevic in 2021. There's been further developments on this in the case of SLN n equals 2 and 3, and the problem of Diophantine approximation by rational matrices, which is also an extremely natural Diophantine approximation problem, and it can even be fit into the framework we're dealing with using the rational points as a lattice in the Adel group. So for Diophantine approximation by rational matrices, a version of the Sarnak density conjecture was established by Blomer, Butkain, and Rolf in 2014, and this bypasses the Ramanujan-Peterson conjecture, just as the Archimedean case bypasses the Selberg conjecture. And this result has very recently been used to establish a non-Archimedean optimal exponent for Diophantine approximation by rational matrices in dimensions 2 and 3 by Jana and Camber. And so there's been some recent activity which tries to leverage the instances where the Sarnak density conjecture, and maybe to be a bit more precise, some variants of it, have been established and get at optimal results, which perhaps on the face of it you would think might require the Selberg or the Ramanujan-Peterson conjecture. But that's really the beauty of Sarnak's density conjecture, that if everything goes well, you can bypass this extremely difficult challenge and get optimal exponents using density rather than a full solution of the conjecture. So let me say just a few more words about this approach. And so the approach deals with uniform quaternion lattices, which is the same thing as uniform irreducible lattices. Well, let's take the group G equals SL2R cross SL2R. And we consider Diophantine approximation, as we already said, on the hyperbolic plane, G mod H, where H is SO2R cross SL2R, using the hyperbolic metric on H2 and the sum of squares norm on G. And as we already mentioned, the unitary representation in L2 naught G mod gamma is a countable sum of irreducible representation pi z tensor pi w, each with finite multiplicity. And here pi z and pi w are irreducible representations of SL2R, so these are well known and fully classified and very approachable. And with some luck, we will be able to control some of their properties. And then we define geometric convolution operators on L2 G mod gamma. That means that these operators will be defined by a certain function on G, and this function will be used to convolve functions on L2 G mod gamma. And it will be used using a specific choice of radial functions on G. And these radial functions on G will be defined by properties of their spherical Fourier transform and its inverse. And the functions, therefore, must will be required to satisfy certain support conditions together with a spherical Fourier transform decay condition. Then we will try to estimate the Hilbert-Schmidt norm of these geometric convolution operators on L2 naught using the pre-trace formula and the density estimate. And so the gist of this, of the problem is going to come to the following. We seek to estimate the trace of the product convolution operator pi g mod gamma FRR acting on L to g mod gamma, where the function FR comma R G1 G2 is F capital R G1 F little r G2. And here we're going to have a large function and a small function. R is a large parameter and little r is a small parameter. And the large R parameter is going to be responsible for the estimate of the size of the element gamma that we will be able to find. And the little parameter R is going to be responsible for the size of the neighborhood of the point where we have been able to transport our orbit. Well, maybe I'll rephrase this. So the size of the small neighborhood, which really is the quality of approximation of our point by the gamma action. And both FR and FR are constructed and estimated using the spherical unitary Fourier transform, as well as its inverse on the group SL2R, as well as the Paley-Wiener theorem for the spherical Fourier transform. And the main challenge is keeping a careful balance between the decay of the spherical transform of the functions and the radii R and R of the balls where they are supported. So that's the key. You have to keep a perfect balance between the requirements here. And the key estimate will be to show that if you look at pairs of representation, pi z, pi w, so here we have pi sigma 1 plus I tau 1, pi sigma 2 plus I tau 2 in the spherical spectrum of G mod gamma, then this sum, which is given by the multiplicity in which these representations occur, times the Fourier transform, the spherical Fourier transform of F capital R and F little r, that this will be balanced in such a way that this will be bounded by B epsilon e to the epsilon r for every positive epsilon. And so here you can see directly, okay, this expression is nothing other than what will come into the computation of the trace of the operator, of the convolution operator. And the trace, of course, is what controls the Hilbert-Schmidt norm. So this would appear naturally in the computation, and you can see both that bounds on the multiplicity will be crucial, as well as complete control over the spherical Fourier transform. And this key estimate is supposed to be proved under the crucial balanced volume condition. The balanced volume condition of the supporting balls in the hyperbolic plane, and the balanced volume condition is the volume of the large ball times the volume of the small ball equals 1. That's the magic condition. And given this inequality, so when the foregoing norm inequality holds, the support conditions on the functions F capital R, F little r makes it possible to solve the underlying inequality with an element gamma in gamma whose norm is bounded by capital R, and such that the distance or the level of approximation d gamma inverse xx naught is less than little r, approximately up to various epsilon and delta and constants, etc. But that's the gist of it. And when the norm bounds hold for the choice of the functions f capital R and fr satisfying the balanced volumes condition, this translates into a Diophantine approximation bound which exactly matches the a priori pigeonhole bound. And so in that case, the result is optimal. Okay. Yes. And so I have a little bit, okay, so maybe one or two more comments. So this becomes a rather concrete problem here. Since the operators are radial, the parameters ZW belong to the principal series or to the complementary series of SL2R, which are parameterized by IT, T real, and S between 0 and 1/2. And if M pi IT cross pi S gamma denote the multiplicity in which the representations appear in L2 naught, then for T positive and sigma between 0 and 1/2, the density estimate for the range of unitary parameters being 0, the interval 0 to T and the interval sigma to 1, states that for all delta positive, the sum over all the multiplicities where the one unitary parameter, the first unitary parameter is between 0 and T, and the second is non-tempered at least to the point, to the degree sigma, the total sum of all of these multiplicities is bounded by a certain power of capital T, which is determined by the level of integrability. And this is the main density estimate used in our analysis, with other ranges of the unitary parameters satisfying similar bounds. And the last thing I'm going to say, for those who are familiar with Sarnak's density conjecture, this expression that we have here, namely T to the power 2, 1 minus 2 sigma, well, the relation between this expression and the integrability exponent of the spherical function of the complementary series, pi sigma, let's say, is explicated by the fact that 1 plus T to 2, 1 minus 2 sigma is the same thing as 1 plus T squared. Yeah, this is not, okay, there's a typo here, but it doesn't matter. 1 plus T squared to the power 2 over P plus sigma, where P plus sigma is the integrability exponent of the complementary series pi sigma. Namely, the least P such that a dense subspace of matrix coefficients in A sigma is in LP SL2. The reason I'm saying that is that if you remember the Sarnak density conjecture, well, the insight that it's based on is that the decay of the multiplicity is given by interpolation. It's given by interpolation between the appearance of the trivial representation once and multiplicities of other representations. And so I wanted to show that in our case, where we have a somewhat more elaborate version of it, it still conforms to Sarnak's heuristics. It's a refinement of the multiplicity bound stated by Sarnak, where this interpolation of the multiplicity was really the key insight. Okay, well, thank you very much for your attention.